kids are in the class?
7.
7, right? Because maybe the rain. People in California aren't used to the rain, I guess. Okay. Yeah, actually there was a chance that we might have parents in the class today, like parents and students, but I kind of thought that wasn't unlikely. That wasn't likely, and indeed, no parents signed up for this class. Okay, so today we're going to go into chapter 4. So chapter 4 is about continuity. Chapter 2, remember, was setting up this stuff about this sort of vocabulary of point set topology, and now we're going to use that to sort of rework everything we knew about continuity before. And actually prove the things that we assumed that we said were true in calculus. Yeah. Okay. So the first thing we're going to do is talk about limits. Okay. So I don't know how limits were defined to you back in calculus. How were limits defined back in calculus? Does anybody remember? Were they defined? Were they just sort of like, as you get closer to this number, your value gets closer to this number, something like that?
Yeah.
Okay, so yeah, so that's sort of like the hand wavy way of defining things, and it's not the mathematical way of defining things. So here's the mathematical way. So let me make sure I get it right here. So okay. So you have two metric spaces, x with its metric, and you have y with its metric. Okay, and you have a set that's sitting inside of x. Okay, so there's like one metric space, there's another metric space, x, y. You have a set here, a set E here, and you have a point that is in the limit. It's a limit point of E. Okay, so maybe E is some sort of open set, right? And P is in the limit. P is the limit point. Okay. Then we can talk about and you have a function going from E to Y. So function f going from E to Y. Okay. So if you're thinking back in terms of calculus, what this is like is that you have some set E, and you have some point. The point doesn't have to be in E, right? So the function is defined. The function is defined on E, but you can still talk about the limit. You can still talk about the limit as the values approach that P, right? The P doesn't have to be in the domain, right? So P need not be necessarily in the domain of F. Okay. So here's how we say. So if there exists a point Q in Y. If there exists a point Q in Y such that given any neighborhood NRQ, such that given any NRQ, there exists a punctured neighborhood. What notation did I use? Oh, I should actually use epsilons and deltas. And so there's given any neighborhood around Q, there's a corresponding punctured neighborhood around E, around P, such that F of that neighborhood lies inside of the epsilon neighborhood, then we say that the limit of f of x as x approaches p is q, and that f has a limit at p. Okay, so I know that's a lot of things to think. Here maybe let me draw the picture let me draw the picture in the calculus way. Okay, so suppose that our set E is these two open is this open interval here with a hole in the middle. Okay, so this hole here in the middle, that's P. Okay, right? And we have something like this, right? And this thing here is our Q. Okay, this thing here is our Q. And what you see is that no matter, right, so this is the, as you get closer to P, your values get closer to Q. What does that mean in a kind of backward sense? It means that if I take any neighborhood around Q, and I say, I want your values to stay inside that neighborhood, so Q plus epsilon, Q minus epsilon. You can find a neighborhood around P. You can find a punctured neighborhood around P in which all the values stay inside there. Okay, all the values. So there's a punctured neighborhood, a punctured, what we call a delta neighborhood, punctured neighborhood around P, where all the values, when you take these values and map them through F, they all stay inside here, right? So like, really what having a limit means is that no matter how close you want to make your outputs to Q, there is a place where that happens. Okay, so like, here's this function, and we say that, right, we say that the limit is, let me make an easier one. Here's this function, say, f of x equals x, and here's the point 5, say, and here's 5, right? And we say that the limit of this function is 5 as x approaches 5, right? What does that mean? That means that if I want my values to stay within one of 5, I can find a place down here. I can find a punctured neighborhood down here, namely from 4 to 6, where all my values stay inside that neighborhood, right? And if I want it to stay within 5.1 and 4.9, that is, if I take an epsilon of 0.1, then I can find a corresponding delta down here that will namely the same value, right? So like, as long as I stay between 4.9 and 5.1, then all my values stay within that tolerance of 5, right? And I can do that no matter what. I can do that no matter what tolerance I'm asked for here. So, like, for the limit to be 5 means that I can make my values as close to 5 as I desire, right? I can make my values as close to 5 as I desire. So no matter what, the way I usually say this is, no matter what tolerance around Q is required. So that's the epsilon. There's a neighborhood, a punctured neighborhood. There's a radius delta in which that tolerance is satisfied. Okay, so that's really what the limit being Q means. That If somebody says, I want you to stay within 0.1 of Q, there's a place where you can do that. If somebody says, I want you to stay within 0.001 of Q, there's a point where you can do that. So, yeah, just to give another example, basically the same example, right? If I have 5 here and 10 here, and I say, I want you to stay within a tolerance of 1, right? Well, what radius will satisfy that tolerance? Think about it for a minute, and talk to each other. Just talk to somebody nearby. Okay. So what's the answer? What's the answer? Anybody? 1/2, right? As long as you stay within, as long as you stay between, 5 plus 1/2 and 5 minus 1/2, then your outputs are going to stay within 1 here, right? And if I took 0.1 here, 10.1, 9.9, how close would I have to be here? What would my to satisfy that tolerance, how close would I have to be here? Go ahead.
0.05.
0.05, right? It would be half of that, right? Because the speed of this is 2, right? The velocity of this is 2. So, as long as you stay within half of epsilon here, then you're okay, right? So if I said I want you to stay between 10 plus epsilon and 10 minus epsilon, what would my delta be down here? None?
Half epsilon.
It would be half of epsilon, right? So as long as I stay between 5 minus epsilon over 2 and 5 plus epsilon over 2, my values are going to be in there. Okay, so you see that. So this is how we define the limit. It's instead of saying as you get closer to here, you get closer to here, we say it in kind of backwards way, that given any closeness, there's a place where that closeness is satisfied. Okay, given any radius up here, given any radius around your target value, there's a radius around your limit point in which the radius up here is satisfied, the tolerance up here is satisfied. Okay, and that's this definition here. Okay, given any epsilon ball, now we do it in the full-blown metric space world, right? Given any epsilon ball, given any epsilon neighborhood around Q, there's a punctured neighborhood around P such that F of that punctured neighborhood is contained inside here. I messed up a little bit. This should be punctured neighborhood intersect E, right? Because the function might not be defined on the whole punctured neighborhood, right? But at least the punctured neighborhood intersect E, intersect the domain. Everything that's reasonable to take a value of, when you take that value, it's contained inside of here. Okay, right? Like over here when I was talking about, right? If I was talking about a half neighborhood, right? If my function is only defined up to here, I can't talk about a full, full interval here. I just talk about the half interval, the intersection with the domain. Okay. Okay. So this is what we mean by limit. Okay. Given any neighborhood, right? Given any neighborhood around Q, there's a punctured neighborhood around P such that everything reasonable, everywhere, wherever the function is defined in that punctured neighborhood, all those values will go inside here. Will satisfy the tolerance. Is that kind of making sense? If we rewrite this in terms of the metric, so we can rewrite this. If there exists a Q in the target space such that given any epsilon, there exists a delta such that if for x and e, the distance of x from P is smaller than delta implies that the distance of f of x from Q is less than epsilon. Then we say that the limit of f of x is Q as x approaches P. Okay, so this is exactly the same statement, right? Given any radius around Q, right? Given any radius around Q, there exists a distance that we're gonna, so that if we're within that distance of P, but not at P itself, right? This thing forces the puncturedness, right? Right. You're looking at points within a delta ball, but not at the center, right? Okay, so that there exists. This is basically saying, right, there exists a punctured delta ball around P, such that when you take the point and map it, the image is within epsilon of Q, right? So f of x is within the epsilon ball of Q, right? So just, if you like to think of it in terms of metric, more in terms of the metric rather than in terms of the neighborhoods, it's the same thing. But yeah. Okay. Okay, so this is the definition of the limit. Okay, I won't say it again. Okay, so just one comment. Like we said before, notice that P need not be in E, right? It just needs to be a limit point of E, right? And even if it is, we don't require that the limit be the value there, right? We don't really care about the value of f of p, right? F of p could be over here, right? Right? F of p could be over here, but all we care about is that there is some value with this property. Okay, and that's something that you're familiar with from calculus, right? That when you have some function like this, right? When you have some function like this, the limit is still 5, right? You don't care what the value, right? Here you've got this function where the value of 5 is, let's say, 10, right? But the limit of the function is still 5, right? As you approach 5, the value of the function approaches. The values of the function approach 5. Okay, so that's all we're saying here. That maybe it could be that the function is not even defined there, and even if it is there, we don't require that this actually be the limit value. Okay. Okay, so. Often when I'm thinking about this, I don't think too much about being in the domain. The main thing is that given a neighborhood around here, given any neighborhood around here, there is a neighborhood around the point where everything gets mapped inside there. Okay, yeah. I mean, it's true. You have to be careful that you are in the domain, but that's sort of like a technicality. Right? The main thing is that you can find these punctured neighborhoods. Right? Given anything over there, you can find a punctured neighborhood over here. Okay. Now let's see how we use this definition to prove some of the basic facts of continuity. Okay. I'm not continuity, of limits. So, so first off, theorem, limits are unique. Okay, so, right, so if you have some, again, you have some pair of metric spaces, and you have, some function, some subset of x, and you have some point in the limit set, limit points, and you have a function going from e to y, and our claim is that that the limit, if the limit as x approaches p exists, equals something, q1, say, and your friend goes into a room and says the limit, if two people go into different rooms and figure out what the limit is, they'll come up with the same value. Okay, then q1 equals q2. Okay, there can be only one point with this property, right? Okay, so here's the picture. Here's the proof by picture. So, like, here's your point P, and let's suppose that Q1 and Q2 are different points. Okay, suppose that each of these guys has the limit property, right? That no matter what epsilon neighborhood you take, you can find a punctured neighborhood here where everything inside here will get mapped inside the epsilon neighborhood. Okay, that will result in a contradiction. So we'll do by contradiction. Okay. Does anybody remember how this is done, or know how this is done, or can you figure out how it's done? So each of these guys has, what's the property? The property is that given any epsilon ball, there is a punctured ball here where everything gets mapped inside there. The whole, right? Everything inside the ball gets mapped inside there, right? In other words, I can make my values as close to Q1 as I desire. I can also make my values as close to Q2 as I desire. How does that lead to a contradiction?
When the neighborhoods around Q1 and Q2 don't intersect. Perfect.
Yeah. So you just say, well, look, since I can make my values as close to Q1 as I desire, let's take my radius to be half of the distance, or to be even more clear, a third of the distance. Right? Take the distance between these two guys, take a third of that, and then take epsilon, so let take epsilon to be a third of that. I know that there's a neighborhood around here where the punctured neighborhood, everything in the punctured neighborhood gets mapped inside here. I also know that there's a punctured neighborhood around it where everything in that punctured neighborhood gets mapped inside here, right? But then the points in the intersection, that is the smaller of the two punctured neighborhoods, will get mapped inside of both of those neighborhoods, right? Anybody in the intersection must be in here and in here, but they're disjoint, contradiction. Yeah?
Is this sort of related to like one-to-one correspondence? How like a map can only be, like points in a map can, like they can only go to one value basically?
No, not quite. Yeah, it's, no, it's really has to do with the definition of the limit, right? This business of you can make it as close to Q1 as you can, as you desire, and you can make it as close to Q2 as you desire. It's not a matter of P gets mapped to Q1 and P gets mapped to Q2, so they must be equal. It's not that at all, actually. Yeah. Yeah. No, it's really, you really have to use the property of use this notion of closeness. Yeah. So so the proof by the written proof is, let's suppose Q1 and Q2 are different. Okay. Then of course the distance between Q1 and Q2 is bigger than 0. Right? That's a property of the metric, right? Whenever you have 2 points, they have positive distance, right? So let epsilon be 1/3, say, let's make it a half. Let epsilon be a half of the distance, right? And then since Q1, right, since the limit of f of x as x approaches P is Q1, we know there exists a delta 1 such that such that f of the punctured delta 1 neighborhood of P is mapped inside of the epsilon neighborhood of Q1. Right. And again, I'm being sloppy. I should say intersect D. Right. Since the limit is Q1, we know that there's a punctured delta neighborhood around P that gets mapped inside the epsilon neighborhood around Q1. Right? Is that okay? Right. And we also know that for for Q2. Right. So I'm just going to say for Qi. Maybe let's similarly for Q2 there exists a delta 2 with the same sort of properties. Okay. Okay. But then consider some point in the neighborhood, the punctured neighborhood of the smaller of the two. Right. Take somebody who's in the smaller of the two neighborhoods, right? Which lies in both of them, right? Then we know that the distance of f of x to Q1 and is smaller than epsilon, right? And the distance of f of x to Q2 is smaller than epsilon, right? Both of those distances, right? F of x has to lie in this thing, and f of x also has to lie in this thing, right? Let me spell out the contradiction. Then the distance of Q1 to Q2 by the triangle inequality is smaller than the distance of Q1 to f of x plus the distance of f of x to Q2, right, by the triangle inequality, right? But each of these things is smaller than epsilon, right, which is smaller than epsilon, smaller than 2 epsilon. Right? Is this okay? Okay. But each of those epsilons, right, was 1/2 of the distance from Q1 to Q2. So this is twice 1/2 of the distance between Q1 and Q2. Right? Which would mean that the distance from Q1 to Q2 is smaller than the distance from Q1 to Q2, which is good. Right? That's not possible. Okay. Right? Right? This is saying that, look, f of x is really 1 point, right? So the distance from here to here being epsilon and the distance from here to here being epsilon means that this is really 1 point, so the distance from Q1 to Q2 is smaller than 2 epsilon, right? Smaller than this plus this, right? Which is 2 epsilon, but that's smaller than the distance from Q1 to Q2, right? Saying that this distance is smaller than, I'm sorry, that this distance is smaller than the sum of these two distances. Okay, so contradiction. Okay, so this is, one thing about limits that you know. Okay, so is that any questions about that? Okay. Okay. Now I'm going to talk about continuity. Continuity. Do you mind if I erase this? Anybody remind? Is it okay? Continuity. Okay, so now we're going to talk about what continuity means. Again, I don't know how continuity was defined back in calculus for you, but it's probably something sort of like some sort of hand-wavy thing. Yes? No? How was continuity defined? Anybody remember? Nobody remembers. Why did we even define it? Yes?
It was like if the limit as x approaches p of f of x equals f at p.
Okay,
then it's
okay.
continuous.
Okay, that's actually a real definition. Yeah. Yeah, that's actually a good definition. High school, and often in high school, those people will say like, you don't have to lift up your pencil or something like that. Yeah. Yeah. Okay, so yeah, that's pretty good. Okay, so here's how we're gonna define it, and it'll look kind of familiar, maybe. So again, right, we've got x and y metric spaces. We've got a function. Sorry, we've got a function from e into y, where e is a subset of x, and we have a point. This time the point is actually in the domain. Okay, right, because we want the function to have a value there, right? Right. We want the function. Right. We have the function should have some value at that point. Okay. So okay. So if here's the definition: if given any epsilon neighborhood around f of p, there exists a delta neighborhood around p such that f of the delta neighborhood intersect e is contained in the epsilon neighborhood. Then we say that f is continuous at p. We say f is continuous at p. Okay. So what's the difference here? Anybody see the difference between this and the limit definition? Remember, the limit of f of x being q as x approached p was that, given any neighborhood around q, there exists a punctured neighborhood around p such that blah, 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 right? So what's the difference? Yeah.
In this case, instead of q, it's f at p.
Yeah, so one we're talking about f of p, right? So this is like saying, and then the second thing is that, anybody see the second part that's different? Charlotte?
None of them are punctured neighborhoods.
We don't care about punctured because we care about what happens at that point, right? We actually do care about what happens at that point, whereas previously we didn't. Okay. Okay. So what you want to observe is that, as a remark, if P is in, if P is also is further, if further, P were a limit point, then what this is saying is that then the above, right? Then f continuous at P is the same thing as saying that the limit of f of x is f of P. Right? Because what this is saying, is that the limit of f of x is the limit of f of x as x approaches P actually is f of P. Right? This is the same. This is basically this stuff here is will imply this thing. Right? Right? Because how would I write? Okay. What does this mean? This means that for all neighborhoods around f of P, there's a punctured neighborhood around f of P such that blah 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 blah. Right? Okay. And you see that this thing is actually stronger than this, right? Because this thing says, given any epsilon neighborhood around f of P, there's a full-blown neighborhood, right? A tonal neighborhood such that this happens. Well, certainly the punctured neighborhood is still going to satisfy this, right? So this is this part is definitely true. Right? If you're continuous at P, that definitely means that the limit of f of x is f of P. Right? Okay. And then going backwards, if the limit of f of x equals f of P, that means that you have the punctured neighborhood, right? Should I write? Maybe I'll write this out a little bit more slowly. So proof of the remark. Okay. So f continuous at P means that given any epsilon neighborhood around f of P, there exists a delta neighborhood around P such that this is contained in that. Right. That's what continuity means. Right. Okay. But that certainly implies that there exists a punctured neighborhood. Punctured neighborhood with that property. Because the full neighborhood has that property already, right? So if when you just throw out a hole, throw out the center point, sure, everything's going to be mapped inside. Everything's going to be mapped inside there, right? Is that clear? Right. Okay. And then going backwards, if we know that if the limit of f of x is f of P as P approaches, as x approaches P, that means that means that, that for all epsilon neighborhoods around f of p, there exists a punctured neighborhood such that f of the punctured neighborhood lies inside the epsilon neighborhood. Right? That's what the limit means, right? That the limit being f of p means that given any epsilon neighborhood around f of p, there's a punctured neighborhood around e that gets mapped inside there. Okay. But what we want is the full neighborhood to be mapped inside there. Right? Why is the full neighborhood mapped inside there? Why is the center point p mapped inside there? Well, right? The center point is p, right? What's f of p? F of p is f of p, which is the center of that neighborhood. So definitely, since f of p lies inside of the epsilon neighborhood, certainly the whole of this thing is mapped. The whole of this thing is mapped into that thing. Right. Okay. So, is this? Are you guys okay? I know this is maybe a lot of notation. Yeah. How are you feeling? Bad? Everybody, how are you? Close your eyes for a second. On a scale of 1 to 5, how are you feeling? 1 is low and 5 is high. How are you feeling? 1 to 5. Oh, okay. Everybody put your fingers down. It's better than I thought. Thank God. Okay. Good. Okay, great. So, yeah. So, right. So, continuity. So, limit means that, given any neighborhood, there's a punctured neighborhood. Given any tolerance, no matter how small, you can find some punctured neighborhood that gets mapped inside there. Continuity means given a neighborhood, no matter how small, you can find an entire neighborhood that gets mapped inside there. Okay, you can find a full neighborhood that gets mapped inside there. Okay, that's the difference. And you see that if the point is in the limit set, then you can express continuity in this way. Okay, in your old the way that you're familiar with. Okay. There's another remark that the author throws in. It's kind of an odd one, about kind of a degenerate case of P being isolated. Okay, if P is an isolated point of E, right? Here's f of P in the other world, right? You take an epsilon neighborhood around it. Now, P is an isolated point, right? So that means that you can find a neighborhood around it where there's nothing else in E, right? There's nothing in E except for the center P, right? So in that case, this whole neighborhood definitely gets mapped inside there, right? Because there's only one point of E of the domain in here, namely P, and that gets mapped to the center, right? So whenever you're an isolated point, the function's automatically continuous there, right? So if it's an isolated point, then f is continuous there. Because you can always find a neighborhood, just take the neighborhood in which P is isolated, right? Take the neighborhood in which P is isolated, that neighborhood gets mapped inside there. So whenever you're isolated, the function is continuous there. But that's kind of that's just like a technical point that you don't really have to worry about for the most part. Like, yeah. Okay. Right, like if you think about back in calculus, what would it mean? Here's your domain. Suppose your domain is like this interval and this point here. What does it mean to be continuous at that point? Right? What does it even mean to be continuous at that point? So we just basically say you're continuous at isolated points. Okay. Okay. 5 minutes. Okay. So here's a theorem that you're probably familiar with. It's like this. You have two functions, f and g, right, going from x to y to z. Okay, and you have some point f that gets mapped to f of p. That point gets mapped to g of f of p. Okay, and you want to show that the composition function. You want to show that the composition. So claim. Right. If f is continuous at p and g is continuous at f of p, then the composition is continuous at p. Okay. So I'm going to be a little sloppy and not worry about domains. Okay. I'm not going to say take the intersection of this domain, blah, blah, blah. Okay. Because it's not the main idea. Okay, so what do you want to show? You want to show that, well, what do you want to show? Remember, you want to show that given any epsilon neighborhood around here, there's a delta neighborhood around here that gets mapped by the composition, right? That gets mapped by the composition inside here, right? That's what it would mean to show continuity of this guy. You know that you can do that for each individual step, right? You know that g is continuous here and f is continuous here. So you know that given g, you know that given the epsilon neighborhood, you can find a neighborhood around here that gets mapped inside there. And you know that given any neighborhood around here, you can find a neighborhood around here that gets mapped inside there. So you just put those two facts together and you get a neighborhood here that gets mapped by the composition inside there. Okay, so that's the idea. So you want to show that given any epsilon neighborhood around g of f of p, 1, 2, 3, there exists a delta neighborhood around p such that the composition maps it into the epsilon neighborhood. Okay, but you say, well, g is continuous at f of p. So, right, so we know that there's some sort of intermediate neighborhood around f of p such that g maps that intermediate neighborhood inside of here. Right? Somebody gives you epsilon neighborhood here. You know that since g is continuous here, you know that there's some eta neighborhood. That gets mapped inside there by g. Right? G will map this thing inside there. That's continuity. Right? F is continuous at p. So there exists a delta neighborhood around p that f maps into the eta neighborhood. Right? F maps the delta neighborhood into the eta neighborhood. Right? So F maps the delta neighborhood into the eta neighborhood. Right? But then, G maps that eta neighborhood into this neighborhood, right? So G composed with F maps the delta neighborhood into the epsilon neighborhood. Right? Because G composed with F, well, you hit this thing with F first, it gets mapped into the eta neighborhood, then you hit it with G, it gets mapped into the epsilon neighborhood. Right? So G composed with F will take this thing into here, and then that will go into here. Right? And so G composed with F is continuous. Right? You wanted to find a neighborhood around here that the composition would map inside the epsilon neighborhood, right? And we were able to do it by using the continuity of G and the continuity of F. Okay. Okay. So yeah, next time we'll talk about a different way of thinking about continuity, which is called the topological definition of continuity, which is really cool. It's like a sort of a different viewpoint. Instead of thinking about what you think about is rather how F inverse behaves on open sets. And it turns out that if F inverse of an open set is always open, then F is continuous. Okay, and this is kind of a way of defining continuity without any reference to a metric. So when you later on take a course in topology, you may have a space in which you have open sets, but you don't have any metric. But you can still talk about continuity using this definition, because you can still think about open sets, and it'll be the inverse image of open sets are always open. And that will be the definition of continuity that you can use in a more general setting. Okay, that's it for today. I will have your exams back next time. I graded most of them over the weekend, or I marked them